Okay, this recording is for molecular geometry. So while we're doing lab in class, I thought that we would at least have something to look at. And today I wanted to go over some molecular geometry. At this point, we've been going over how to arrange atoms around a central atom in a molecule. These only apply to covalent species in a two-dimensional structure. So the next logical progression or step in that process would be to take it from 2 dimensions into 3 dimensions. So molecular geometry takes our Lewis structures and converts them into a more likely 3-dimensional structure where the central atom is surrounded by these terminal atoms, and we consider the bonded pairs and the lone pairs for our geometry. So I'll just start here. It says the specific 3-dimensional arrangements of atoms and molecules are referred to as molecular geometry. We'll also define this as the positions of the nuclei in a molecule. This is the general shape that it takes on, and it governs how things will participate in their properties with other species. It'll determine whether something is polar or non-polar, and also what it dissolves in, and many more things in our next unit. Shape is dictated by both bonded and lone pairs around a central atom, and how those both repel and attract one another. Well, how they repel each other in their space that they are given. Molecular geometry is important for looking at properties of different chemicals. All of this is based on what is called the VSEPR theory. The VSEPR theory is the valence shell electron pair repulsion model. And again, this is a theory, which is going to bring some limitations at some point, but this theory suggests that electrons will arrange themselves around a central atom in a position to be as far apart from each other as possible. And that's why you'll see here it says that they will minimize repulsion. It says in a molecule that has more than 2 valence shell electron pairs, the molecules tend to be on opposite sides of each other of the central atom. So this will be for, I said more than, with 2 electron pairs, so 180 degrees. 3 electron pairs, and you'll find them in what's called a trigonal planar shape. 4 electron pairs, and they're in what's called a tetrahedral shape. 5 electron pairs are in what's called a trigonal bipyramidal shape. In 6 electron pairs, we have what's called an octahedron. I think I spelled that wrong. I'll just go octahedral. Sorry about that. Octahedral shape. So what I did is I took these pictures of balloons to show you that these are the favorable shapes that they take on. I'll do the same thing in class when we're together this week, where you'll see that these shapes that we're talking about are just natural shapes that things take on to be as far apart from each other as possible. And so you'll see here 2 balloons take on a linear geometry, 180 degrees from each other, 3 a trigonal planar geometry, 120 degrees from each other, 4 balloons where you might think they would take on a square of 90 degrees. We actually find that they take on a geometry that has even more than 90 degrees of an angle, and that is your tetrahedral shape at 109.5 degrees. Add 5 balloons and you get 2 planes of bonding. Here we have what's called an equatorial region, that's the center, and then you have the top and the bottom, looks like an axis. Those are called our axial positions. And then we see the same thing with 6 balloons. Again, this was called our trigonal bipyramidal, and it's called trigonal because we have a triangular base with a we have a triangular base of 2 pyramids, top and bottom, and then an octahedral because we have 8 faces in that last 6 balloon structure. Now these are our 6, 1, 2, 3, 4, 5 major shapes. Anything else will be a derivation of this shape. Now when we look at these, the first thing we'll want to do is we'll want to talk about things that have bonded pairs only, and then we will progress into have lone pairs, because lone pairs take up more space and cause distortions. Although they will be very similar structures than what we'll start with, we'll just see a distortion of that structure, and you'll see that in just a little bit. And that's kind of what we're saying here. When we see these bonds come in, instead of having an angle, you'll see it be called a less than angle, as the distortion causes that angle to shrink. And again, we'll talk about that as we get there. And then we're going to kind of go through these in just a second. I don't need to get through that yet. I'll talk about those. I wanted to show you some pictures of these. So this is called a ball and stick figure because you essentially have a geometry that would show the bonds as sticks, and then at the end you would have these spheres that would indicate the actual structures. And I have a lot of these things in class that I'll show you whenever we go over them. These are all of our structures. The main structures: linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and your octahedral. It's funny that when we get down to this pentagonal bipyramidal, even though it is a possible structure, I will tell you that I've never seen a compound that falls into this, so neither will you in this year. Anything that is to the right of this first column, these are things that are variations of those normal structures or those base structures that are based on, you'll see the big blue section there, electron pairs, adding more distortion, and you'll notice the angles being less than. So I think that if we look at this, I don't want to go down too far. I think the best thing for us to do is to actually just start doing these. And so I have one here, it says, where's my CH4, but I want to move over to my other screen because I feel like it would make a lot more sense if I showed you these instead of just putting them on a screen. So let me move over. I'm going to screen share over. Oops, let me do that. Okay, I'm going to screen share to my other device. Because what we're going to do is we're going to look at that molecular geometry, that arrangement around a central atom taking on as a shape that will minimize repulsion. Again, this is based on the Vesper theory, valence, shell, electron pair, repulsion model. So in order to do this, we have 3 steps we're going to follow. Number 1, draw the Lewis structure. So you'll see that everything is based off of what we just did, drawing a Lewis structure. Number 2, count the total number of electron pairs around the central atom. Then arrange the terminal atoms in such a way as to minimize repulsion. And then number 3, it's going to say describe the molecular geometry in terms of angular agreement of bonding pairs. Probably should add that. Now that seems like a lot, and to be quite honest, just like I had said with Lewis structures, I really don't memorize per se these, but you'll see that as I keep doing them, it really becomes a similar stepwise process over and over again. So let's start, and what makes the most sense to do, molecules in which, remember these are all covalent, the central atom has no lone pairs. Remember, it is the central atom that determines the structure. And so we're just going to go through and do some of these structures. But remember, as I mentioned this before, and I should probably mention it over and over again, as we go through this and we talk about bonding pairs, for the sake of geometries, all bonds are considered a bonding pair. So if you have a single bond, it's one bonding pair. A double bond is one bonding pair, and a triple bond is one bonding pair. Now there's a reason for this, and we'll get to it maybe either towards the end of this week or the beginning of next. And so we'll start with some examples. The first one is BeCl2. BeCl2. Well, BeCl2 will fall into one of those Lewis structures, that is an exception. If you're watching this on Monday, we haven't gotten to this yet. If you're watching this Wednesday, we did it on Tuesday. And so beryllium chloride actually looks like this. So beryllium, let's go through it. Beryllium is in group 2 on the periodic table, 2 electrons. Chlorine is in group 7, 2 times 7. So this is 16 electrons. So again, we draw the Lewis structure, BeCl2. Now you might put in double bonds if you haven't seen Tuesday's lecture yet. And we're going to tell you on Tuesday why those double bonds don't occur according to what's called the electroneutrality principle. But for now, let's just leave it as you see it here. This is the Lewis structure for beryllium chloride. If you did put double bonds in, it actually wouldn't change anything. So the first step is to draw the Lewis structure. The second step is to count pairs. There are 1, 2 bonded pairs. Now, again, this is only the central atom that we'll be talking about. There are no lone pairs on the central atom. So the central atom has only 2 lines coming off of it, and they are all attached to something. And all of these examples will, thus the title, molecules in which the central atom has no lone pairs. Next thing we're going to do is we're going to find a way that it can arrange itself in such a way as to be as far apart from each other as possible. And so here we find our handout with this. 2 bonded pairs, no lone pairs. This gives us a shape of something that is linear. So you can see an example there. And so when we draw this, we're going to draw beryllium to chlorine. Bond angle is 180 degrees, and it is considered linear. Okay, far apart from each other as possible. And you would have seen this on our notes. It considers it being AX2, A being the central atom, X2 being those 2 atoms surrounding the central atom. Example number 2. Example number 2 will also fall into that lecture on Wednesday, Tuesday. So again, if you're looking at this on Monday, there'll just be something about this that we're going to reinforce on Tuesday, and that's BF3. Boron has 3 electrons in its outer shell. There are 3 fluorines times 7. That's 24 total electrons. To do a Lewis structure, going to set this up. So you'll notice that what we did is we counted those electrons in the outer shell. We put in all single bonds to those atoms. Then we satisfied their octets, and what we were left with was 24 electrons minus 24 is 0. Now you might think there are bonded pairs. We're going to talk about why that's not according to the electroneutrality principle and formal charges. But again, for now, even if you would put it in, it wouldn't change anything. There are 3 bonded pairs and no lone pairs. So the question becomes, how do 3 things arrange themselves in such a way around that central atom to be as far apart from each other as possible? So when we go down, it's the next one down, 3, 0. That's our trigonal planar. And so it's a triangle, that's what the trigonal means, in one plane, trigonal planar. Now, again, these are called ball and stick figures. In a space-filling model, you would see that it looks slightly different in terms of the actual space between those atoms, but the space-filling models are also a lot more difficult to sometimes see the bond angles. All 3 bond angles are the same. They are 120 degrees. And again, this is a trigonal planar. Number 3. Number 3 is the first one that's in your notes. That's CH4. 4 electrons in the outer shell for carbon, 4 times the 1 electron in the outer shell for hydrogen. That's 8. We draw our Lewis structure, carbon with the 4 hydrogens surrounding it. We get 4 bonded pairs and no lone pairs. So you'll see that every one of these always starts the same way. Determine the Lewis structure. Once the Lewis structure is determined, we count the number of lone pairs and bonded pairs, and we find the geometry that agrees with that structure itself. When I go down here, I'll see that 4 bonded pairs and no lone pairs is something that is tetrahedral. Now, tetrahedral is a tough one to draw. Actually depends on how you look at it. We see it in 2 different ways. This is the way that I'm most familiar with it, and that is to have carbon, hydrogen, 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 and oh, I'm so sorry about that. I should have warned you. That one probably came out of the video in 3 dimensions, nearly poked you in the eye. Man, that was really, really crazy. Sorry about that. That's a fantastic 3-dimensional drawing. I'm sure that as you look at that, you're like, wow, that's like coming out of the screen. And I agree. Fantastic 3-dimensional drawing of 109.5 degrees for a tetrahedral. Hold on, I gotta wipe my eye. Feel like maybe it's watering from the hydrogen poking out from the screen. Wow, what a fantastic 3-dimensional drawing. Number 4, PCl5. We also will have addressed this in our discussion on Friday. Again, exceptions to the octet rule will be our one of our other things that we look at, where phosphorus, 5 electrons, 7 times the 5 chlorines, that's a total of 40 electrons. You have phosphorus surrounded by 5 chlorines. And we did talk about this last week and on Tuesday. If you watching this on Monday, you're going to say, oh, we'll get into this tomorrow. If you're watching on Wednesday, you say, oh, we talked about this yesterday. We're going to talk about things that have more than an octet on the central atom. In phosphorus, having an available p subshell can have more than an octet. Because it can have more than an octet, here you'll see it with 10 electrons around the central atom. But again, for our purposes, more importantly, 5 bonded pairs and no lone pairs. I go down and I look for 5 bonded pairs and no lone pairs. Got to go to the next page to find that, and you'll see it right here. 5, 0 is trigonal bipyramidal. When we're to do that, we got to draw 2 planes. So here's P, there's Cl, and there's Cl. Oh, that didn't look like a Cl at all. Now I will warn you, be drawing something in 3 dimensions here. Don't worry, this one's going to be away from us. There's a Cl. Oops. Okay. Public service announcement. We have an orbital coming out of the screen at us. Ah, right in the eye. Got me again. Gee whiz. And so there we have our trigonal bipyramidal. So with this, what you'll see is the reason we call it trigonal. Here we have a triangle, so it makes sense here that around our base would be angles of 180. Thinking of the other one, sorry, of 120. And then the ones that we see here, 180 degrees, these are called axial. And again, as I mentioned, these are all in one plane. If I spelled it right. Equatorial. Now, if you look at it, you will find that these do make an interesting pyramid. Now, you can't really see it there. See if I can get you one here. Again, warning, 3-dimensional structure coming your way. Oops. So if you look at that, what you'll see is here, here, right? And obviously here, here, and here. That is our get it going here. That is our pyramid. And there's a pyramid on the top and the bottom, so that's why it's called bipyramidal. Has a triangular base, so that's why it's called trigonal. Okay, number 5. Number 5 is SF6. Sulfur has 6 fluorines times 7, so a total of 48 electrons. Again, we draw the Lewis structure for this. That's S and 1, 2, 3, 4, 5, 6. 6 fluorines. You count them all up, that's 48 electrons. Oof, that's 6 bonded pairs and no lone pairs. You arrange these in such a way as to be as far apart from each other as possible. When you go down 6 bonded pairs and no lone pairs is my octahedral. And so we have our central atom of sulfur. Ooh, that wasn't good at all. Here is a fluorine. Again, warning. Ooh, these things just don't draw well. Fluorine. So now what you'll see is these equatorial ones are all in one plane and they take on the shape of a square. So these are 90 degrees. Ooh. And then we get our 2 axial position fluorines. These are 180 degrees. And so now what we're left with is what's called an octahedral. Okay? An octahedral, where our bond angles are 90 and 180. So what we need to be able to do is to first draw all of these structures, name them, and come up with their bond angles. And so what we've done is we've gone through all of the main structures. I want to look at in our few final minutes together here. I want to look at, my pen back. Move this over, molecules. Or ions in which the central atom has lone pairs. Molecules or ions where the central atom has lone pairs. A couple of things we need to know: lone pairs cause distortions in angles. That's important. So we take our ideal geometry, our standard geometries, and they'll generally be a less than angle. Okay. Another thing we need to know is lone pairs take up more space than bonded pairs and have more repulsive forces. So I need to give you some repulsion strengths. So I want to look at the strengths of repulsive forces. And so these would be the weakest of our repulsive forces, and that would be our right here. Bonded pair. Bonded pair. Those are less than lone pair, bonded pair, and those are less than lone pair, lone pair. So the greatest repulsion would occur between two lone pairs, but you'll see in either case, once we add a lone pair, the repulsive forces increase. So let's also start with some examples and then we'll finish it up for the day. First one we're going to look at is SO2. We started that with our resonance structures. Remember SO2 having 6 plus 2 times 6 is 18 electrons. Here's what you will find. It doesn't matter how many resonance structures there are. Sulfur dioxide looks like this. No matter which structure I pick, they're all the same. Remember, single, double, and triple bonds are all considered one bonded pair. So I have 2 bonded pairs and 1 lone pair. 2 bonded pairs and 1 lone pair, I go to a 3-structure geometry. So here's our 3-structure geometry. That was that trigonal planar. But because there isn't a bonded pair, we remove that bonded pair and we replace it with a lone pair. This is my SO2, where remember in my 3 structure, my trigonal planar, the angle was 120, so the angle will now be less than 120. The name of this is being called bent. And if you wanted, you could draw the lone pair in, although you don't need to do so. You don't need to do that at all. Could, but you don't need to. Okay, number 2. Next one is ammonia, NH3. 5 plus 3 times 1 is 8. And so we have nitrogen and our 3 hydrogens and our lone pair. So again, we see here 3 bonded pairs and 1 lone pair. We go to our 4 pairs, that's our tetrahedral structure. Oh, I should have warned you. Sorry about that. And then what we do is we remove one of our bonded pairs. When I do that, there's my nitrogen and followed by my 3 hydrogens. Again, that's where my lone pair is, but I don't need to show that. The angles for these were 109.5 when it was tetrahedral. Now that there is distortion, it's less than 109.5, and this is a pyramidal structure as the structure itself takes on a pyramidal shape. Okay. 3. H2O. 2 times 1 plus 6 is 8 electrons. Here I have O and the 2 H's. And so I put my leftover electrons on the central atom, even if doing so creates more than an octet. And when I do so, I get, again, the 2 bonded pairs, 2 the hydrogens, and now 2 lone pairs. I still have 4 pairs of electrons. Oh, I really got to keep warning you about that. Sorry. Now let's get rid of those bonded pairs. And then what we're left with is something. Here is O and the 2 H's. The angle is no longer less than 1, well, it's not 109.5, it's less than 109.5. The 2 lone pairs actually make it, in some cases, we'll call it much, much less than 109.5, although I'd be happy if you knew it was less than 109.5. The angle for this one's actually 104.5. Not that you, again, need to know that. But again, we see a distorted angle and another different version of something that is bent, as we saw with SO2. Okay, number 4 is SF4. SF4, when I look at this, it's 6 plus 4 times 7. And so 6 plus 28 is 34 electrons. And so I have my SF4. That's 32 electrons. I add the 2 to the central atom, even if doing so creates more than an octet. What does that give me? Well, 4 bonded pairs and 1 lone pair. So now we will take on a 5 bonded structure. Oh, sorry again. Now when I do that, in a trigonal bipyramidal structure, the lone pairs come in the equatorial region. And so when I get this, I have my SF4. And this one's a hard one to tell. When you look at the name of it, you'll see that it's known as an unsymmetrical tetrahedron. Angles, by the way, are less, so less than 120, less than 180. But really, very few, if anyone, refers to this as an unsymmetrical tetrahedron. They take this, they flip it on its side, and they see something that looks like this. Well, something that looks like that, that's a seesaw. And so this is our seesaw shape. Okay? That is our seesaw shape. Okay. Last one, only a few more. Don't want to get into too many of these, just because I know that we're going a little bit long in our video, but figured that would make sense. So let's then figure out our last one. Last one here. Let's see, what do we got? How about XeF4? XeF4. As we know, there aren't very many elements that have more than where noble gases make compounds. So not many of those, but there actually is one with this one, XeF4. And to be quite honest, as the elements get large, as we go down the noble gases, you find that they are more likely to make compounds. Xenon makes a few of them. It's only helium that doesn't make any that we know of so far. So Xe has 8 electrons. 4 times 7 is 28. So that's 36 electrons. We have Xe and F4. That leaves me 32, so 2 lone pairs. I like to just show those as dots. Now, by the way, when we do this, if there's 1 electron instead of 2, so let's say this had 35 instead of 36, we would still put that as a lone pair, even though it's not a pair, because even 1 electron will occupy that non-bonded orbital. This has 4 bonded pairs, 2 lone pairs. We get that 6 electron pair structure. Looks something like that. We take off 2 of them. Well, in this case, instead of taking away the equatorial, we take away the axial. They look like this. Now that they come away, we have a, as I mentioned before, a square in one plane, so a square planar. In this case, the top and bottom actually repel each other, and so we get 90 degrees in this square planar molecule. There aren't many more that do that. I think that, I mean, I have plenty more to show us, but I don't know that it's good to go into those with just all of the time we've done so far. So as we talk about molecular geometry, we have many more of these to do, so we will do some more examples for sure, as we try to find out more 3-dimensional arrangements of atoms around central atoms using this set of common structures that you see over here. At some point, we will go through every one of them, even put one on the end that has examples off to the side. But again, all of these are based off of lone pairs and bonded pairs. We took these steps from now going to Lewis structures into looking at molecular geometries. The next step of this is to add to it polarity and hybridization, and then looking at molecules with more than one central atom. I think that's a good place for us to stop for this today. And I hope that that will help us as we continue to move towards finishing this being chapter 9 in our book.